Yeah, thank you everyone for coming. It's my pleasure to introduce today's speaker, Mr. Alper Çakan, or Çakan. Okay, I never managed to read your last name. Okay, Alper is a PhD student at the Carnegie Mellon University, supervised by Professor Rico Goyle. He's interested in quantum cryptography. He's an expert in unclonable crypto. He has published several papers at top venues, including TCC, QIP, and QCrypt. Today, he's going to share with us his recent publication at QCrypt this year on the exciting novel notion of quantum fire. Without further ado, please join me welcoming him.
Thank you for the introduction, and thank you for hosting me at your seminar. So today I'm going to be talking about public key quantum fire and key fire from classical oracles. This is a recent joint work with Vipul Goyal and Amri Shmueli. By the way, is everyone familiar, at least a little, with basic crypto and basic quantum information, or to adjust the level of the talk? Anyone not familiar at all with quantum information? Okay, then I think we're good. Okay. So we all know the very basic principle called no-cloning principle, which is one of the fundamental principles of quantum mechanics. It says that given an unknown quantum state, no physical process can create two copies of this unknown quantum state. This is a very old result from the 80s. And another very basic principle of quantum mechanics, maybe this is a little less well known, it's called the no teleportation principle. This says that given an unknown quantum state, no physical process can create a classical string from which the original state can be reconstructed. So this principle is also called the no-telegraphing principle because, as we all know, there's this thing called quantum teleportation where you can actually send some unknown quantum state over a classical channel by sending a classical measurement result. But of course, that requires entanglement between these two adversaries or these two parties. But here in the no teleportation principle or the no telegraphing principle, we are considering two parties that are not entangled. So to prevent confusion, I will also use the terminology introduced by Nehoran and Zhandry, and I will call this the no telegraphing principle. So actually, these two simple principles are equivalent to each other in the following sense. No cloning principle implies a no telegraphing principle because if you could telegraph some state to clone it, you can actually just pretend to telegraph it. You run the telegraphing procedure that you know that succeeds, and you get some classical string, and it's easy to copy classical strings. And you run your reconstruction procedure for your telegraphing algorithm twice, and you just end up with the two copies of the unknown quantum state. So that would violate the no cloning principle. So no cloning implies no telegraphing. There's also an implication on the other direction. So if you could actually clone some unknown quantum state, you can keep cloning it until you have sufficiently many copies for something called a tomography procedure, which receives some number of copies of a quantum state and gives you a classical description of the state. This is essentially a density matrix for this state. So by this reduction, no telegraphing also implies no cloning. There's another related principle called the no interactive telegraphing principle, which is essentially a generalization of the no telegraphing principle. And this was introduced by my work joined with Vipul Goyal, Chandra Zhang, and Joy Ribeiro. But I'm sure some other people must have observed it before, but I didn't see any other prior work where it was formalized. But this essentially says that given an unknown quantum state, this time we have two parties that are not entangled, but we don't have a single message from the first party to the second party. These parties can interact classically for any number of times, and they can send messages of any length. And still, the other party will not be able to reconstruct the original state on the other side.
So,
yes.
The previous version, no telegraphy principle, just
Yes.
consider one message.
Yes, exactly. You mean this one, right?
Oh, so your version, what you proved is like information theoretically you proved it, or it's just a conjecture?
This one?
Yeah, you prove it.
Yeah, this is information theoretically proven.
But if you are doing an impossibility, doesn't non-interactive case implies impossibility?
So I'm saying that this is a stronger result that implies the previous result.
Okay.
Right. Yes. So interestingly, even the stronger version is actually implied by the original no-cloning principle, but the reduction this time is a little bit more subtle. So what we do is what we call a transcript duplication argument. So suppose for a contradiction that you could actually interactively transfer this unknown quantum state. So to clone this unknown state, we do the following argument. We just keep running two independent copies of this second party here. And we keep running independent copies until we get the exact same message that is supposed to be sent from the second party to the first party. And once we end up with the exact same transcript twice, we are also storing the internal final quantum state of the second adversary. And once we are done with this, we just run the first adversary once because we only have a single copy of the initial unknown quantum state. But this is okay because we are, again, conditioning on getting the same transcript twice for the second adversary. So we just need to answer a single query by the second adversary. So we just run the first adversary once. And this allows us to end up with two final internal states of the second adversary. And we know that, by assumption, we know that this interactive telegraphing procedure succeeds. So we know that this internal state can be used to reconstruct the original state. So with these two copies, we just run the reconstruction procedure and we end up with the two copies of the unknown state. So right now, the state of the affairs is that we know that no cloning implies no interactive telegraphing, which trivially implies no telegraphing, and no telegraphing implies no cloning. So essentially, all of these rules or principles of quantum mechanics are actually equivalent to each other. But there's one fundamental issue in these equivalences or reductions so far, that all of these equivalences are actually inefficient reductions. For example, when going from no-telegraphing to no-cloning, we said that we will perform a state tomography, which provably requires exponentially many copies of the unknown quantum state. And going from no-cloning to no-interactive telegraphing, we made this transcript duplication argument, but the messages sent from the second party to the first party can be of any length. So to condition on getting the same transcript twice, we will have to keep running the second adversary possibly exponentially many times. So in both directions, we are doing an inefficient reduction. But in real life, of course, especially for crypto, we are more interested in efficient reductions because we are more interested in polynomial time processes. So the question is, for the states that we can actually prepare in real time and the processes that we can apply in real time, by this, I mean the polynomial time preparable states and polynomial time procedures. Are these principles of quantum mechanics really equivalent? So previous work of Nehoran and Zhandry showed, relative to a quantum unitary oracle, that there's a collection of states that cannot be telegraphed efficiently with a single message. So it satisfies this initial version of the no-telegraphing principle that we saw, but it can be cloned efficiently. So for this collection of states, relative to this unitary oracle, no-telegraphing principle does not imply the no-cloning principle. A more recent work of Bostanci, Nehoran, and Zhandry gave a candidate classical oracle separation of no-cloning from, again, one message no-telegraphing principle. But unfortunately, they didn't give a proof. They just heuristically argue that this classical oracle should satisfy the separation between these two principles. So in terms of actually provable separations we have so far, we only know a quantum unitary oracle separation. But again, another recent work by Agarwal and Kundu showed that sometimes quantum unitary oracle separations can give us just plain wrong results and separations. For example, they show some separations between various complexity classes that are true according to unitary oracles, but in the real life, actually, the inclusion of these complexity classes are in the opposite direction. So,
Did they publish this paper?
Sorry?
Is this paper published at that?
Agarwal Kundu? This is like a very recent paper, so probably in submission somewhere.
Formal paper or just some short notes, like 3 pages? So.
No, I think it's a very nice formal paper. It's like probably 30 pages or so. Yeah. Okay. So as I said, so far we only have a quantum unitary oracle separation, which can be somewhat misleading. So the question is, can we actually separate these principles using classical oracles? So in this work, we answer this question positively, and we show that relative to a quantum accessible classical oracle, there's a collection of states that cannot be telegraphed, and even interactively. So even in the unitary oracle separation, previous to this was only a separation between one message telegraphing and cloning. Here we show that these states cannot be telegraphed even interactively, but they can be cloned efficiently. So this says that no interactive telegraphing does not imply no cloning for efficient processes, at least relative to classical oracles. Okay, so beyond the separation between these two principles of quantum mechanics in an efficient world, we actually have more applications of our techniques and results in this paper. So our first application is about this recent concrete cryptographic hardness assumptions introduced by the recent work of Pfefferman, Gauss, Sinha, and Yuan. So there's been a recent line of work in quantum crypto about considering cryptographic assumptions in a quantum world where we assume that all the parties have quantum computers. And people have been able to show that some cryptographic hardness assumptions can survive even if there's no classical crypto. For example, we already know that for classical crypto, existence of one-way functions is a minimal assumption. If we don't have one-way functions, we will not have any crypto at all in classical world. But the question is, are things different in a quantum world where people have quantum computers? And people have shown various oracle separations where, again, there's no classical crypto, but there's some quantum crypto. But even more recently, people have started coming up with concrete hardness assumptions that could be useful in a quantum world, even if there's no classical crypto. So to explain this better, for example, when I say existence of one-way functions, that is a assumption about a primitive, but that's not really a concrete assumption from which we can build crypto. But there are also concrete assumptions like hardness of factoring or hardness of learning with errors and so on. So recently, people have tried to come up with concrete assumptions from which we can really build crypto. So this recent work has proposed two different assumptions for quantum crypto, so-called computational no-cloning assumption and computational no-learning assumption. So the computational no-cloning assumption that they have proposed says that, both of these are defined relative to some collection of circuits, quantum circuits. And here, when I say random circuit, I will mean a quantum circuit sampled uniformly at random from this collection of quantum circuits. And to make this assumption fully concrete, they also specify some concrete collections of quantum circuits. So the computational cloning assumption says that given k copies of a state output by some random circuit from this family of circuits, no efficient adversary can output k+1 copies of this state. And they give a construction of a very simple quantum commitment scheme, a quantum commitment to classical bits, assume that is secure, assuming this computational cloning assumption. And they also introduced this assumption called the computational no-learning assumption. And this says that given k copies of a state, and k can be any polynomial, that is output by some random circuit that's sampled uniformly at random from some collection of quantum circuits, no efficient adversary can output a classical description from which this original state can be reconstructed. From this assumption, they give constructions of one-way state generators and quantum signatures for the classical methods.
So in the second assumption, the quantum primacy game.
This one?
Just means a quantum circuit output cannot be replicated by a classical. I mean, I know better about the difference.
Right. So you're saying this could be equivalent to like proof of quantumness, or?
Yeah. If you
right.
have to do crypto from this assumption, can you also claim, okay, I can do crypto from proof of quantum?
Right. I think this is a little different because here we're talking about like quantum states, right? So this is kind of saying that quantum states are kind of like stronger than classical states or classical strings. But for proof of quantumness, for POQ, you need some like stuff that's all classical messages, right?
Yeah. Or classical reference to verify. So
Yeah, exactly. Right. Also, I think this doesn't say anything about verifiability, right?
efficient verifiability.
Yeah. All right, this doesn't say anything about efficient verifiability.
So that the first one also implies long-stage generator.
This one? Yeah, actually, so I think I mentioned this here. Yeah, the no cloning assumption is stronger. It implies the no learning assumption. So as you said, like this also gives all of the stuff here. Right. And these are the formal definitions of these hardness assumptions that I just mentioned. And as I was just saying, they also show that computational no cloning implies computational no learning. And the proof is not too hard. It's essentially the same as the equivalency between no cloning and no telegraphing. Essentially the same argument. Okay, so they also conjecture that, they show that no cloning applies no learning. But it could be the case that no learning also implies no cloning, and they could be equivalent, just like the equivalency between no cloning principle and no telegraphing principle. But they conjecture that the computational no learning assumption is actually weaker. So they conjecture that there could be a classical Oracle separation where the no learning assumption holds, but the no cloning assumption does not hold. And we actually answer that question positively. Again, we show relative to a quantum accessible classical oracle, there's a circuit family for which the computational no learning assumption holds, but the computational no cloning is not satisfied. So this means that no learning is a weaker assumption and it's more likely to hold. So this is essentially a more conservative assumption. Okay. So this first application was about separating some new hardness assumptions in a quantum world where classical crypto possibly does not exist. We also have a second application, and this is more about advanced quantum crypto, where we're okay with classical crypto existing and we're not necessarily trying to minimize our cryptographic assumptions, but we want to get some security guarantees that are provably impossible to get with classical computers, no matter what kind of assumption you make, what kind of cryptographic assumption you make. So before delving into our definition and construction, let me talk a bit about this high-level issue about crypto. So right now I'm going to talk a bit about classical crypto. So in most of classical crypto, we assume that the adversaries are attacking our constructions through well-defined channels. For example, in an encryption scheme, for example, public key encryption scheme security game, we're just assuming that the adversary sees various ciphertexts and they also see our public key and they're trying to later on decrypt some challenge ciphertext. Or for signatures, the adversary sees various signatures and verification key, and later on they try to come up with a new signature. And you can generalize this to various other cryptographic primitives. But crucially, all of these security models assume that the adversary has no information at all about our secret keys. But the question is this assumption, is this modeling of adversarial attacks is actually realistic? And there's a long line of research in classical crypto where people have argued that this is actually not a realistic security model because people, especially people on the practical side of crypto, have shown that in real life we can do some attacks that do not conform to the security model. And we can group these various attacks that do not conform to this model under the umbrella of side channel attacks. So people have, for example, shown that by measuring the time spent by a classical computer storing the secret key of some cryptographic scheme, you can actually learn some partial information about the secret key itself. Again, this is not captured at all by usual security games because we are assuming that the adversary has no information at all about the secret key. People have also shown that by analyzing, for example, the electromagnetic radiation emitted by the classical computer that's storing the secret keys of a cryptographic scheme, you can actually learn possibly some bits of the secret key. And they have also shown that for various cryptographic schemes that are widely used in practice, even just learning some side information through these side channel attacks can actually let you break the security guarantees that are usually satisfied by the cryptographic scheme. So the question is, how do we actually keep our secret keys secure so that we can get our security notions back even when the adversaries are able to mount these side channel attacks? Again, as I said, people have considered this question for a long time. In classical crypto, there's this whole area of research called the leakage resilient crypto, where people have tried to design schemes that are secure even against various side channel attacks. But again, the question is we're trying to show various security guarantees in a formal mathematical model. And all of these attacks I've mentioned so far are kind of more on the practical side that could be somehow hard to formalize. So to solve this issue and bring the problem back to the realm of theoretical crypto, people have tried to define various models that try to capture all of these attacks. And one of the most commonly studied model to capture side channel attacks is the so-called bounded leakage model. So in the bounded leakage model, we assume that the adversary applies some function, arbitrary, efficiently computed function of its choice, to our secret key. And we require that the usual security guarantee, like, for example, inability to distinguish between an encryption of 0 versus encryption of 1, still applies against such an adversary that learns this bounded amount of information about the secret key. And usually, actually not usually, always in this model, in the bounded leakage model, we're assuming that the adversary's choice of the function that will be applied to the secret key has a bounded output length. So there are various ways to justify this model. For example, when you're learning some information through like timing attack or electromagnetic radiation analysis attack, it's kind of acceptable that you can assume that the adversary will only learn maybe a few bits of information. But actually people, again, on the practical side of things, have shown that sometimes this assumption is not true. But still, on the theoretical side, most of the leakage resilient crypto makes this assumption. And the main reason for this assumption, at least on the theoretical side, is that if you don't make this assumption, if you're not bounding the output length of this adversarial leakage function, there's actually nothing we can do in the classical crypto, because the adversary can just output the classical secret key in full as its leakage, and there's nothing we can do. So one question is, just like quantum information helps us get classically impossible security guarantees like quantum money, the question is, can quantum information, can it help us get new, stronger security guarantees for the question of side channel attacks? And in a previous work with Goyali, Zhang, and Ribeiro, we showed how to construct a so-called unbounded leakage resilient public key encryption scheme, where the secret key of the PKE scheme is encoded into a quantum state. Okay, so let me formally define our model. So in unbounded leakage resilience, we imagine a PKE scheme, a public key encryption scheme, where we encode the secret key into a quantum state. And our first requirement is correctness, which is essentially the same as the usual classical PKE correctness. We require that this quantum encoding of the secret key can decrypt any encryption with overwhelming probability. One implication of this correctness guarantee is that we can actually keep using this quantum secret key to decrypt various different ciphertexts. Because as we know, in quantum information, once you measure a quantum state, you usually disturb it or like destroy it in an irreversible way. But this correctness guarantee says that when you're measuring the ciphertext, you have a single determined output that you get with overwhelming probability when you actually apply this honest measurement procedure. And by a principle called, or by a theorem called gentle measurement lemma, this says that you can actually implement this decryption measurement in a specific way so that your quantum state is not disturbed at all. So this means that you decrypt your ciphertext, you get your message, and your quantum state didn't change at all, so you can just keep decrypting other ciphertexts. So this was the correctness part. And for security that models various side channel attacks, we consider the following security game. So we consider a challenger that samples the keys of the scheme and encodes the secret key into a quantum state. And we consider an efficient adversary that receives this public key, and it specifies a leakage measurement circuit. So this will be a efficient, a polytime quantum circuit with full classical output that will be applied to the quantum secret key. So essentially, the adversary is measuring the quantum secret key. And it receives this measurement result, and we end up with a post-measurement result state. and the adversary also receives the measurement outcome. Then adaptively, it keeps specifying measurement circuits or leakage circuits that are then applied to the post-measurement state from the previous round, and the adversary can continue this for any polynomial number of rounds. And again, the leakage outputs here, the measurement results, can be of any polynomial length. It can be much longer than the size of the quantum secret key itself. For example, the quantum secret key could be of size n squared, whereas the adversary could be obtaining leakage for n to the 100 rounds, where each leakage result is also n to the 100 bits. So this is much stronger than the classical case where you necessarily need to assume that the adversary's leakage measurement or the leakage function has a small output size. And after the adversary obtains its leakage, it receives either an encryption of 0 or 1, and it tries to guess which one it is, and we require that it can do no better than essential random guessing. And also, since we're modeling this as a measurement circuit, this also essentially captures the various side channel attacks we saw here, all of which are essentially just measurements. Okay, so in terms of achieving this unbounded leakage resilience security, again, my previous work with Goyal, Zhang, and Ribeiro, we have shown that assuming indistinguishability obfuscation and hardness of learning with errors, we showed how to construct a public key encryption scheme that satisfies this unbounded leakage resilience security. And even more recently with Vipul Goyal, we showed how to construct, this time assuming indistinguishability obfuscation and existence of any one-way function primitive, we showed how to construct unbounded leakage resilience schemes for any puncturable cryptographic functionality. So this also captures public key encryption, identity-based encryption, functional encryption, and essentially most of the crypto that you can imagine. So let me also talk a bit about a related security notion called copy protection security. So copy protection security is essentially a functional version of the quantum money primitives that essentially relies on the no-cloning principle of quantum mechanics. So for copy protection, we consider this time, again, encoding a secret key of some decryption scheme into a quantum state. And in the security game, the adversary receives this quantum state, and it tries to create two entangled quantum adversaries that should both be able to use this decryption key. And these adversaries later receive either an encryption of 0 or 1, and they're trying to decrypt at the same time. And we require that they cannot decrypt at the same time with probability better than random guessing, essentially. So here our baseline success probability is 1/2, because one trivial attack is that since you do get the honest secret key initially, you can give the secret key directly to one of the adversaries, and the other one can just guess randomly. So even though there are like two independent adversaries here, still our baseline success probability is 1/2 instead of 1/4. And essentially this security guarantee says that you cannot create like two copies of this quantum secret key. Essentially there will only be like one key at all times, and the other adversary will just try to guess randomly. Okay, so as I said, the security notions of copy protection and leakage resilience are somewhat related. In our previous construction with Goyal, Zhang, and Ribeiro, and even in our more previous work, the constructions we give are actually, they satisfy both of these security notions at the same time. In CGLR, we use a construction from Colangelo, Zhandry that they initially gave for constructing copy-protected decryption keys for public key encryption. And in our more recent publication, we give a new construction, but we explicitly show that through different proofs, we show that our construction satisfies both the copy protection security and the leakage resilience security. So to summarize, so far, all of the constructions essentially satisfy both of these security notions at the same time. So the question is it possible that these security notions are just equivalent? So that would mean that we don't actually need to like repeatedly prove these security notions separately, because as I said, like in this work we showed these security proofs separately, and again here we use the same construction from the CLLZ paper, but we give quite a different security proof for leakage resilience compared to the proof that they gave for copy protection security. So if these security notions were equivalent, we could just prove one of them, and we didn't have to spend any more time trying to prove the other one. And on the other side of the coin, actually, so this copy protection security notion is especially useful when you're trying to, for example, sell a piece of software, like for example, video game or say Microsoft Excel, to some parties for some money, and you don't want them to pirate this program and distribute it for free. So that's essentially when you use this copy protection constructions. But for leakage resilience, we have a completely different motivation, where we're just trying to, we create our own scheme, we create our own software, and we're just trying to securely store it on our computer so that our security notions are not broken by side channel attacks. So here we don't necessarily need copy protection, and in fact, it would be better in most cases if we did not have copy protection, if we could clone our leakage resilient key. Because, for example, later on, we might want to transfer this key to another computer or another server, or for example, we might want to store this key for a long time, and we might want to keep refreshing this key to prevent decoherence. An important point here is that we cannot store the classical description key of the key as a separate backup, because that would defeat the whole purpose of storing it as a quantum key to obtain these unbound leakage resilient security guarantees. So in this work, we show that relative to, again, quantum accessible classical oracle, there's a scheme that satisfies unbounded leakage resilience security for any unlearnable functionality, but the keys are not unclonable. In fact, we give an efficient cloning procedure for these keys. And this is essentially a tight result, because by unlearnable functionality, I mean a functionality that you cannot create a classical description of it just by interacting with this functionality in an input-output behavior. And if you have a learnable functionality, there's no way to achieve leakage resilient security, because in this leakage resilience game, the leakage adversary can just keep querying and evaluating this functionality at various points to essentially learn a classical description of it. So this is essentially a tight result in the classical oracle model. So through this result, at least in an oracle model, we show the feasibility of obtaining unbounded leakage resilient schemes with clonable keys, which would make them much more practical compared to the existing unbounded leakage resilient schemes. And also this shows that these security notions are not equivalent. Unbounded leakage resilience does not imply copy protection, which means that we cannot just get away with proving the security for one notion and assume that the other one also holds.
This is a classically structured oracle.
Yes, yes.
That oracle.
Sorry?
That oracle, do you explain for me once?
This one?
Yeah, that's the oracle. That's for the scaling concept.
So maybe on a very high level, it's kind of similar, but yeah, to get this clonability while still satisfying the leakage resilience, we need to do much more work. Okay, so before talking about constructions of these separations and schemes that satisfy unbounded leakage resilience and so on, let me talk about this cryptographic formalization of the separation between no-telegraphing and no-cloning. So we model the separation through this cryptographic primitive called quantifier, which was again introduced implicitly in the work of Nehoran and Zhandry and explicitly in the recent work of Bostanci, Nehoran and Zhandry. So in a quantifier scheme, we consider these four efficient algorithms. We have a setup algorithm which essentially outputs a public key and a secret key. And the secret key can be used to create a so-called flame state, which will be clonable, but it cannot be converted into a classical string. And we have this cloning algorithm that receives an honest flame state and creates a perfect copy of this state with the serial number onto another quantum register. And finally, we all have this verification algorithm, which essentially, so this is a little stronger than the previous separations we talked about between no-telegraphing and no-cloning, because here we're also considering a verifiability aspect with a public key. this verification algorithm receives the public key and some alleged flame state with some supposed serial number, and it outputs 0 or 1 saying that this is actually that flame state, the honest flame state, or no. And we have two different correctness requirements. As I said, we call cloning correctness, which says that given an honest flame state, the clone algorithm outputs a perfect copy of this state and onto another register. And we have the verification correctness that says that given an honest state, honest flame state, or a copy of it, a clone of it, the verification algorithm outputs 1 with overwhelming probability. And to formalize the no-telegraphing aspect of this scheme, we consider this security game. In the security game, we have a challenger that samples the keys of the scheme, and it creates this initial flame state using the secret key, and this flame state has some kind of serial number. Then this efficient adversary receives the initial flame state, which we know that it can clone using the honest cloning algorithm. Then it tries to transfer this state onto another adversary, and both of these adversaries are efficient, but they're not entangled, and they're only interacting classically. And they keep interacting for any polynomial number of rounds, and they can exchange messages of any polynomial length. And at the end of this game, this second adversary tries to output some state, which is then verified by the challenger with respect to the original serial number of the original flame state. And the challenger outputs 1 if the verification passes correctly. And we say we record that for any efficient pair of adversaries, the probability of getting one output in the security game, the probability of the adversaries winning the game, is negligible.
So what's the purpose of the serial number?
For the serial number?
Get a more architectural from the application perspective. Why do we need a serial number?
Right. So I think maybe one point of serial number is that you can also consider a variation where the adversary is generating the state itself. So it's like publicly generatable through some common reference string.
Yeah.
But still, it shouldn't be able to transfer the state that it has generated itself to another adversary.
But according to this definition, it looks like once you have one flame, you can make multiple copies of it.
Yes.
I think the serial number doesn't play any role in this sense, right?
Yeah, I think you're right that here we can, yes, here we can probably remove the serial number because here there's a secret key. But again, we can also consider a generalization where there's like a CRS. I can write here, right?
Yeah.
So you can consider a version. This is called like collision resistant quantum fire, where there's like a CRS, common reference string generated by some procedure, right? And some adversary receives the CRS, and it generates some fire state, some serial number. And later on, A1 sends the serial number to the challenger, and A1 and A2 interact, and A2 tries to output some state that will pass verification for the original serial number.
I see. You think that in internal application, it's important to require that, sure, you can clone, but you cannot clone for the same serial number.
Yes, exactly. Because here, again, like this A2 also receives the CRS, right? So it can create like its own version of a flame state with some different serial number. Because like everyone can create flame states here. So here, like it's important to consider no telegraphing with respect to the original state. Does that make sense? But here, as you said, you can probably ignore the serial number because you have a secret key, so it's not like anyone can generate states. And this is like a stronger version. Right. So as a generalization of quantum fire, we also consider a primitive called quantum key fire. So this is essentially a functional version of the quantum fire states, just like the relationship between quantum money and copy protection. So in quantum Keyfire, again, we have a algorithm for generating flame states, but this time this generation algorithm also takes as input some function. And this algorithm outputs a flame state along with some serial number. Again, we have a efficient cloning algorithm that receives a flame state and creates a perfect copy of this flame state onto another register. And finally, this time instead of a verification algorithm, we have a evaluation algorithm that receives a flame state and some input to the function that is encoded by the flame state and outputs some evaluation result. Again, we have the cloning correctness. It says that clone algorithm works as we expect. And instead of verification correctness for Keyfire, we have evaluation correctness, which says that when you create a flame state encoding some functionality, when you run evaluation on this flame state on some input, you do get the correct output f of x for the function that is being encoded by the flame state. And for the no-telegraphing aspect, we require that the following security guarantee holds. We consider the security experiment where the challenger samples a function from some distribution of functions and encodes this function into a quantum state. Again, the adversary receives this quantum state and classically interacts with another adversary. And later on, it receives the second adversary receives a challenge input from some high entropy distribution, and it tries to evaluate this original functionality on this challenge input. And the challenger verifies if this output is correct relative to some predicate and relative to the original function. And the challenger outputs 1 if this predicate passes relative to the output of the adversary. And we record that no efficient adversary can win this game with probability better than negligible. Again, in this work, relative to a quantum accessible classical oracle, we show that there exists a quantum keyfire scheme for any unlearnable functionality. Okay. Any questions so far about the definitions before moving on to the construction?
So the notion was first implicitly proposed by Bostanci, Zhandry et al.
Which one?
The
Quantifier?
quantifier.
Quantifier was proposed implicitly by Nehoran and Zhandry.
So which paper first like explicitly defined it?
Quantifier was first explicitly defined by Bostanci, Nehoran and Zhandry, but they only consider like this state type of game where you're trying to transfer the whole state.
Yes.
And actually, I think they also do not consider an interactive adversary. They also just one message. So
your definition, can you explain the difference between your definition and this one?
My definition, you mean this one?
Yeah.
Right. So this is essentially like the difference between quantum money and copy protection, right? So this original definition is weaker than our definition. So here this says that you receive the state and you're trying to transfer the whole state to the other side, right?
Yeah.
But in our definition, you receive again some state, and this allows you to, for example, decrypt some ciphertext, right? So this is essentially an encoding of some secret key of some PKE scheme.
But do you still keep the quantum affair key generation algorithm to have a public key, secret key? You don't have this anymore.
You mean for Keyfire?
In your fire is keyed, right? Your fire is
yes,
keyed.
yes.
So this Spark algorithm doesn't need to take it to SK as input.
So here, this function, you can consider that as some kind of secret key, right?
So
this Spark takes as input some function, right?
Okay.
So this could be like the decryption key of a PKE scheme.
Okay.
So it gives you a quantum key that lets you decrypt ciphertexts, for example. And in the security game, you're trying to essentially transfer this functionality to the other side. And this is stronger because if you could transfer the whole state, then you can also trivially transfer the functionality, right?
Yeah.
So this is actually stronger.
Yeah.
But this essentially captures this amount of leakage resilience security we talked about.
So to me, this looks like the complementary notion of unclonable. Uh, say that. It's complementary to certifiable deletion in some sense. Um, Here I'm talking about the original notion quantifier. You allow people to copy, but
Yes.
to copy you just need to have an initial copy.
Yes.
You want to. I think for this one, like, the correctness is also non-trivial. For example, for
Cloning correctness, you mean?
yeah, the correctness, meaning that once you have one copy, you can copy arbitrarily. This is also non-trivial.
Yeah, exactly. Yeah. I think later on maybe I have the cloning algorithm. So this is like the cloning algorithm for our
Okay.
scheme, right? As you can see, it's not easy.
Yeah. Then I'm wondering, like, when you define uh, the the definition in the previous slide,
This one?
yeah, to me, I think here you care more about the security
Yes.
instead of correctness, right?
So that's we actually care about both, right? So we record this, and separately we record this.
Yeah. I mean,
Yeah.
why? I can see the motivation for the security because you want to use it to model leakage test.
Yes.
But why do you want like in the real world applications is correctness important?
You mean it's cloning correctness? What do you mean? Is it important?
Correctness here just says, if I understand correct, says if you have one copy, you can make multiple copies.
Yes.
This, I mean, in the application of leakage resilience crypto,
Yes.
this something like orthogonal or extra.
Yes, it's extra. You're right.
The original motivation when Zhandry defined this notion, I think he also in his application, I would guess he need correctness in a more essential way than you.
You mean for quantifier itself?
Yeah.
Ye-
I feel like why he defined this correctness, like he has some application in mind, right?
So you're saying like, what's the application for cloning for quantifier?
Yeah.
I guess their motivation is similar, right? They want to get like this leakage resilience without getting unclonability.
Well, then I guess I would have to say passing, like why you need correctness for leakage test. If the setting is just I have a secret key, I don't care if I can make multiple copies of it or not. I just care if I have classical leakage, will I?
Yes, so I think there's like two motivations for that. I think maybe I mentioned it somewhere here. Right. So one motivation for considering this notion is like um, this copy protection and leakage resilience. So far, it seems that they are almost equivalent, right? All the constructions that satisfy one of them also satisfies the other one. So can we just like in the future, when you come up with a construction for example, copy protection, can you automatically say that this also satisfies leakage resilience, right? You wouldn't have to do a different proof. So far, for example, in this work, we had to do like two separate proofs. Each of them is like 15 different pages.
Yeah.
That's a lot of work. Again, this is like two separate proofs and like two separate papers. So do we have to keep doing this, or can we just say that when you prove one of them, the other one is automatic? Right?
But for this purpose, still, I see you need a security guarantee. But typically, correctness is for to achieve your desired functionality, right?
Right. So you're saying that to right. So you're saying that to get this, you can also do something like this. You show some scheme where you have like leakage resilience, but you have a copy protection attack, not necessarily copy correctness, but you just have some attack where you can clone with like probability 1 over pn, right? Is that what you mean?
Not that complicated. It seems to me that in the definition of public key quantifier,
Yeah.
if you just drop the correctness requirement, it'll still be good enough for capturing leakage radius.
Yes. But again, we add cloning to essentially show that this is not implied by to show that copy protection is not implied by the leakage resilience security.
Yeah, yeah, I agree. They are orthogonal requirements. I just don't find the motivation to define correctness. Maybe we can discuss it.
Okay, yeah, we can. Maybe another motivation is that, so aside from the separation aspect, another motivation is that, again, let's say that you only care about the leakage resilience security, but you cannot store the classical description, right?
Yeah.
So you should delete it because otherwise there's no point in storing it as a quantum state. So you only have a quantum state that encodes your secret key.
Yeah.
But maybe later on you want to use it in a different computer, right? You want to give it to your friend or give it to someone who's joining your company. You want to give them the decryption key. But if it's unclonable or if it's a quantum state, in general, you cannot make another copy of it and give it to someone else, right?
Yeah.
So there's some kind of like unwanted side effect of having a unbounded leakage resilient key where you also get unclonability. But this is bad if you only care about the leakage resilient security. So this is like an additional feature when you have clonability. This says that you can give it to some other person later on, or another applications maybe like you can keep refreshing your quantum state, right?
Yeah. Yeah.
So there's like less decoherence. You can just keep cloning it to keep it alive.
Yeah.
I guess that's the feature aspect of this correctness.
Yeah. Then my question would be in the final result you mentioned.
Yeah.
Of the slide right after definition. Can you go to that one?
Which one?
What is it? Yeah, this is our main result, right? For this result,
Yeah.
do you use correctness in an essential way? Can I just prove this result even if I consider a public key quantifier definition without correctness?
I mean, when you say public key quantifier without correctness, you mean there's no cloning, then there's no point to call it quantifier, right? You're just thinking of a scheme with quantum keys that satisfies leakage resilience.
Yeah, yeah, yeah. Can I recover this result for that weaker notion?
I mean, that's we already have that, right? You don't even need oracles for that. We have leakage resilience for essentially a large class of functionalities. But again, the quantum key here is unclonable. So if you want to send it to other people, that's not going to happen. You cannot refresh it.
Yeah, 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 sure.
Yeah, think of it like this. For example, you can have PKE, but you can also have PKE with homomorphism, right? That's like an additional feature. So here we have leakage resilient schemes with the additional feature of clonability of the key.
Yeah, yeah, that I understand. I just was trying to see how essential that part plays a role in the result you.
Right, I would say it's quite essential. Yeah.
Okay.
Guess we don't have too much time. I will just give like a high level overview of the construction. Okay, so one of our main building blocks is this primitive called one-shot signatures that was introduced by Amos, Giorgio, Kiais, and Zhandry. So in one-shot signatures, we have this for efficient algorithms. There's a setup algorithm that outputs a common reference string that will be available to all the honest parties and the adversaries. And there's a quantum key generation algorithm that receives this common reference string and outputs a quantum signing key. And we also have a signing algorithm using this signing key. It outputs a signature for this message that you input to the algorithm. And we, again, have a verification algorithm that verifies alleged signatures. And here, along with the quantum signing key, you also get a verification key that corresponds to this signing key. And the main security notion we require in one-shot signatures is that given this common reference string, which is again available to everyone, this says that like everyone can generate their signature keys, but no one should be able to generate two different signatures, for two different messages relative to the same verification key. So you can create your verification key along with some signing key, and with that signing key, you can sign any message you want. But with the same verification key, you cannot sign two different messages. So this also implicitly means that this verification key, so this signing key you generate here cannot be cloned. And the recent breakthrough work of Mellon and Zhandry showed how to construct one-shot signatures in the classical oracle model. Okay, so let me give a very high-level sketch of our quantifier construction. In our construction, the flame states that are generated by the Spark algorithm are just purified one-shot signature signing keys. So we essentially run this key generation algorithm, but we don't measure the verification key register to get a classical verification key. We just keep it in superposition. And the cloning oracle for our quantum fire scheme will be essentially an encrypted version of the oracles that let you generate signing keys for the one-shot signature scheme. So essentially, you will have the oracles that you have for this generation algorithm, but they, in some sense, they will be encrypted. And to be able to run this oracle, you will need to essentially verify that you initially have an initial signing key. And this verification more formally will be by secret sharing the outputs of this key generation oracle into two separate oracles, one of which verifies signatures for message 0, and the other one verifies signatures for message 1, relative to the same verification key. And to run this key generation algorithm, you will first run this first oracle by signing the message 0, and then you will copy your output to some register, and then you will essentially rewind your signing key, and you will then sign the message 1 with the same verification key to get the other share of the output of the key generation oracle. But as I said, the main security notion for one-shot signature says that you cannot actually sign two different messages with the same verification key. But the trick here, the important part here, is that we're not actually making any measurements. So we're signing in superposition, and then we're rewinding. And by the gentle measurement lemma, this will be fine, and this will not, the correctness part will not violate the security of the one-shot signature scheme.
So this cloning oracle is a quantum oracle, not classical.
It's actually a classical oracle.
That's right in this topic.
Exactly, yes, yes. More formally, I actually have the definitions of the oracles here. So for Spark, we will have some random functions as part of the oracles. And we will also set up a sample an instance of the one-shot signature scheme. And we first construct this O0 oracle, which essentially verifies signatures for the message all zeros, and outputs a random function, which is like a signature on the verification key, and this input that will be passed to another oracle. And this oracle essentially outputs a signature on this verification key and this input Z. And we will have another oracle that verifies one-shot signatures for the message 1, and this will output like an independent signature, again on the verification key and your input Z. So essentially, your input Z will be some input to the actual key generation oracle of the one-shot signature scheme. And here you're trying to sign your input that you want to enter to the other oracle by first signing all zeros, and obtaining this H0 signature, and then signing all ones, and then obtaining this H1 signature. And finally, we have this third oracle to which you input your signatures relative to H0 and H1, and your actual input that you want to pass to the actual key generation of the one-shot signature oracle. And after verifying both signatures, this oracle outputs the actual output of the OSS oracle, the one-shot signature oracle. And essentially, all of these oracles, along with this common reference string of the one-shot signature scheme, will be your serial number for the quantum fire state. Again, we're kind of assuming that here you can output classical oracles as a classical string, but this is just a simplification. And through standard tricks, you can make it so that you're just outputting a regular classical string, and there's a single global oracle, classical oracle. And finally, to generate the fire state itself, the quantum state, the quantum part of the fire state itself, you run the key generation oracle of the one-shot signature scheme in superposition without measuring the verification register. So this is essentially the signing algorithm of the quantum key fire. Again, here I'm considering this key fire notion instead of the fire notion because the key fire is stronger. And specifically here, we're considering a key fire scheme for a signing functionality that lets you get a clonable quantum state with which you can sign different messages, but no leakage resilience adversary can obtain enough information to sign a random message. And here to sign, you essentially just sign with the one-shot signature signing key. And to clone, so I don't think we have enough time to go over the details of the cloning algorithm, but essentially you run your one-shot signature quantum key generation algorithm in superposition. And again, this is kind of encrypted. You do not have direct access to this key generation oracle. But using your initial state, you create signatures for your actual inputs to the key generation oracle, and you sign them for both this H0 and H1. And with this final oracle, you input both signatures, and that lets you get the actual output of the key generation oracle, with which you can complete your key generation procedure for the one-shot signature scheme. Okay, let me give a very high-level quick proof sketch for the untelegraphable proof. So for a simplified case, let's assume for now that the second adversary that's trying to receive this quantum fire state through classical interaction with the first adversary, let's assume that the second adversary does not have access to the signing oracle and the key generation oracle of the one-shot signature scheme, but it only has access to the signature verification oracle of the one-shot signature scheme. And again, to simplify, I will only consider a single message from the first adversary to the second adversary. So suppose for a contradiction that you can actually transfer this flame state using a single message, then we can actually do the following attack to the one-shot signature scheme. We run the first adversary on the flame state and we receive our classical message, and then we keep running our second adversary multiple times to get many different signatures with possibly different verification keys. And for one-shot signatures, we show this new security guarantee that we call strong signature incompressibility security, that says that an adversary that has access to all of the oracles of the one-shot signature scheme still cannot pack too many different verification keys along with valid signatures into a classical string of polynomial size. So by this security guarantee that we show, you can actually conclude that once you're running the second stage adversary multiple times on this message from the first stage adversary, eventually you will get the same verification key twice. But once you get the same verification key twice with different signatures, a signature for 0 and signature for 1, you're essentially violating the security of the one-shot signature scheme, which lets us conclude the security of the quantum fire scheme. But of course, here we made a lot of simplifications. In the actual proof, we also show how to handle things. Then the second stage adversary also has access to all of the oracles, and then they can communicate for multiple rounds. And I think that should be now.
Any questions? I have no questions. Wait, let me ask one.
Yeah.
So I have a question regarding the proof. Basically, your oracle allows the particle signing key of the one-shot signature to in purified manner.
Yes.
So that's always the honest party, right? Who has the signing key.
What do you mean the honest party?
When you consider security, the adversary does the adversary get quantum access to a signing oracle of the one-shot signature?
Yeah. In the foolproof, everyone has access, quantum access to all of the oracles.
My question is like, one-shot signature, if you give me the purified access to the signing oracle, I can always sign something and then unconclude it and then sign another thing. It loses its one-time guarantee, one-shot guarantee. At a very high level, why stop? Sorry.
So you're saying that this could be a problem for what?
I mean, you use one-shot signature because you need its security guarantee, which means like as long as you generate a signature, then you cannot generate one more.
Yes.
Right. But this relies on the fact that you give, for example, you generate signature and you give it to me in a classical way.
Yes.
But if I allow you to give me some quantum data, then I will help you to uncompute it. Then you will lose the guarantee of.
Right. So this is kind of interesting that here, for example, for quantum fire and quantum key fire, we do not really require one-timeness or one-shotness notion, right?
So then why in the security proof, like, why you use it as a building block?
Yeah, it's kind of unexpected, right?
Yeah.
You're using this one-timeness notion to get this like repeatedly usable key. So I don't really have a like intuitive answer why this works, but it just works when you do the proof. But essentially, okay, maybe I can say this. So essentially, one-shot signatures gives you a way of preparing some quantum state without knowing the classical description of this quantum state. For quantum fire, since you require clonability, you need a way to prepare quantum states, right? But you shouldn't learn the classical description of this quantum state because otherwise you cannot get this leakage resilience guarantee. You will just like learn the classical description of the state when running the cloning, and you will send this classical description to the other guy.
So
Does that make sense?
you use it to ensure that if you have some quantum state, you have to store it in the quantum manner as long as you collapse it. Now the one-time signature security guarantee will say that you cannot generate a different copy.
Kind of, I guess, on a very, very high level, yes.
Sure. Thank you. Yeah, let's give him a response. Yeah.
Thanks.